Thanks for giving me the opportunity to speak today. So I'm going to talk about the need to really take into account model errors to diagnose particularly changes in atmospheric circulation. So the key messages I want to try and get across is that models can have very different responses, even opposite responses to the same forcings. So they definitely can't all be right. But this provides an opportunity, I think, to exploit these model differences to narrow the uncertainties. And the final message that's very important is that taking models at face value and seeking consensus could leave society unprepared for impending extremes. So I'm going to start off with this nice paper by Blackforth and Fife. So the upper panel here shows observed changes in U700 winds from the ERA 5 analysis, and the bottom panel shows the multi-model CMIP 6 mean. And what you can see is that there is some hint of a similar pattern in the multi-model mean, but the magnitude is way too small compared to what's actually been observed. And actually, so these crosses here show where none of the ensemble members, 303 ensemble members, captured the same magnitude of the trend as seen in the observations. So potentially there could be just a weak signal in the models, but it's not quite as simple as that for this reason, and that's because the models can have opposite responses. So what I'm showing here is the NAO response to natural forcings, and I'm looking at 31-year rolling means, and the observations are in black, and this is standardized now. And I'm showing two different models, CANI SM5 and CNRM CM6.1 in orange. And what you can see is that these models have opposite responses to these natural forcings, so solar and volcanic forcings. They're potentially highly correlated with the observation, so especially CANI SM5 has a correlation of nearly 0.7. Whereas CNRM has a negative correlation, a significant negative correlation. So I want to try to understand why that is. So what I'm looking at here is the regression between Earth's energy imbalance, EEI, and zonal mean zonal wind, U, again on the 31-year timescale in these natural simulations. And what you can see that there is a similar horseshoe shape band of increased zonal wind seen in both the models, but actually where this increase intersects the surface is fundamentally different in these two models. So in CANI SM5, it represents a poleward shift of the jets and the winds, whereas in CNRM, it's actually an equatorward shift of these winds. So why might that be? So what I'm looking at here is the same thing, but now regression against zonal mean temperature. And you can see that when you have a positive energy imbalance, the troposphere warms and the stratosphere cools, essentially. And that creates a gradient at around the tropopause level that will shift the winds. But where that gradient sits relative to the jet, so the jet here is this magenta blob, and where that gradient sits relative to the jet is different in these two models. So in CANI SM5, that gradient essentially sits poleward side of the jet, consistent with a poleward shift of the winds, whereas in CNRM, it sits on the equatorward side of the jet, consistent with an equator shift of the winds when we have a positive energy imbalance. So why might that be? And the fundamental difference between these two models is background water vapor. And water vapor is fundamentally important in the climate system, and it's the reason why the stratosphere cools, essentially, because the radiation can escape freely to space. So what I'm plotting here, this green dot, so the contour is a particular water vapor contour level, and this green dot is where that contour intersects 200 hectopascals. Yeah, that level. And what you can see is that in CNRM, that water vapor contour is equatorward of the jet location, whereas in CANI-SM5 is poleward of the jet location. So I think this explains some of the differences between these two models. So a poleward location of the water vapor contour would be consistent with a poleward shift of the winds, and equatorward location of the water vapor contour would be consistent with an equatorward shift of the winds. So there are many more models that perform these historical natural simulations. And so what you can see is if we plot all of those, and what I'm looking at here is the jet shift related to Earth's energy imbalance against this hydropause latitude relative to the jet. So just go back to explain what that is. So it's essentially it's the difference between the green blob and the purple blob. So we're defining the hydropause now as the kind of differentiating between the troposphere and the stratosphere in terms of water vapor. So you can see that there is a high correlation, significant correlation across the models when we look at this hydropause latitude relative to the jet compared to the jet latitude shift for a positive energy imbalance. And the observations are slightly more poleward, if anything, compared to all of the models. So this suggests that the real world would have a poleward shift with a positive energy imbalance, and potentially greater than is seen in the models. So this allows us to develop an emergent constraint through the ensemble regression of Bracegirdle and Stevenson, such that generally that we would give higher weights to models that are closer to the observations, and negative weights can be given to models that actually shift the jet in the wrong direction. So when we apply this constraint to the model simulations now, this is still the natural simulations. If we just take the multi-model mean at face value, then we get the plot on the left here, which has a very low correlation with the observations, whereas the constrained correlation now is significant, and you can see that there is some variability. I should say that there is a signal-to-noise error in these constrained simulations, such that they need to be scaled by this factor, the ratio of predictable signals, which is about 4, to achieve in realistic simulations. And the other thing to notice in this, that I'll come back to later, is that although we see the variability, it's slightly shifted compared to the observations there. So the minimum in these natural simulations is around about 1980, whereas the minimum in the observations is just for 1960 and these 31-year rolling means. So what we want to do is look at the projections, the future projections. So we need to include all the forcings for this. So what this shows is some of the models for the historical simulations plus the SSP 245 projections. And what you can see is there's a full range of uncertainty here. So some of the models show an increase in the NAO, some of them show a decrease in the NAO, some of them show little change in the NAO. Some of them actually are significantly correlated with the observations over the historical period. So MIROC 6 and UK ESM, these two in particular, are significantly correlated, but they do show very different projections, future projections. So this pink one is MIROC 6 and UK ESM is this kind of light blue one. So, but we can apply the same constraint that we derived for the natural simulations to these historical simulations as well. And so on the left is taken the unweighted multi-model mean, and that doesn't show a significant correlation with the observations. Whereas on the right, we now, when we do this constraint, we have a significant correlation with the observations. Again, it needs scaling by this factor around about 4, the ratio of predictable signals. And then when we want to look at the projections, again, taking the models at face value, there is some distinction between the different scenarios. So we have the SSP 585, the high greenhouse gas and concentration scenario, the medium mitigation SSP 245, and the strong mitigation SSP 126. But when we apply this constraint now, we get very different projections, future projections, such that in the high concentration of greenhouse gas scenario, SSP 245, the projection now is for unprecedented values of the multi-decadal NAO. And you can really see the impact of mitigation now. So in SSP 245, mitigation starts to kick in around about 2030 or so, and you can see the decrease in the NAO that arrives then. And in SSP 126, mitigation is much earlier, and you can see the impact of that. So what's the mechanism for these changes? So what I'm plotting here is rolling means, Hofmuller plots of rolling mean temperature at the 200 hectopascal level relative to the previous 30-year climatology. So what you can see, if you look at the natural simulations, is that clearly there is an impact of volcanoes that cool this level of the atmosphere. So there were several volcanoes that went off. So Agung, El Chichon, and Pinatubo, and the accumulated effect of those is to cool this level, and that would produce an equatorward shift of the jet and a negative NAO. Whereas in the real situation where we have increases in greenhouse gases now, so the minimum that we get now because of the effect of the greenhouse gases and the volcanic eruptions together, the minimum occurs earlier than it does in just the natural simulations. And I think that's what explains why the natural simulations had this minimum in the NAO around about 1980, whereas in the real world and these constrained simulations with all forcings, that minimum occurs around about 1960. And then if you look at the projections, what you can see is that in the high concentration of greenhouse gas projection, SSP 224, SSP 585, you know, we just see continued warming of this the temperatures at 200 hectopascal. Whereas when we start to get mitigation, then we start to get some cooling, and in the stronger mitigation scenario, that cooling occurs much earlier.
Doug, you're at 15 minutes.
Perfect. So just to summarize them, so I've shown you that models can have very different, even opposite responses to the same forcings. So they definitely can't all be right. I showed that some of these differences can be explained by background water vapor differences in the models, and that's what controls the latitude of heating in the upper troposphere. I think this actually provides an opportunity for us to exploit these model differences and narrow the uncertainties in future projections. In terms of the mechanism, so this this constraint, by doing this, we get a constrained time series that now correlates highly with the observations over the historical period. And the mechanism is that volcanoes cool the upper troposphere, leading to an equator shift of the jet and a negative NAO, whereas greenhouse gases warm the upper troposphere, leading to a poleward shift of the jet and a positive NAO. These simulations suggest that the NAO could increase to unprecedented levels never seen before under the high concentration of greenhouse gas scenario, but this can be avoided with mitigation. And the final point is, as I said before, taking models at face value and seeking consensus could potentially leave society unprepared for impending extremes. Okay, thank you very much.
Thanks, Doug. Has anyone got any questions that they want to ask? I don't see anything in the chat at the moment, but anyone want to ask a question? I did have a question, actually, a very quick one.
Okay.
You know, in that the Eddie showed that plot where you've got the NAO response, and there's a big deviation between a lot of the models, and they showed that like one of the HAD-GEM ones was kind of close to the observations. What is it? I'm not a modeler, so I'm interested to know what is it that drives all this massive deviation between the models compared to the observations, and would they be? Then I'd probably ask is, would they be constrained better if you had better observations?
Well,
or more observational data.
That's an interesting point, actually. So the one thing that we have observed, right back to 1850, actually is the NAO. So you know, we have the best observations of that than of anything, I would say. And in terms of what is causing the model differences, then I think, you know, as I said, some of the differences are explained by the differences in background water vapor, which are very different in the different models. And that's what can cause the opposite shifts of the jet to the same forcings.